right, so this lesson is going to be on calculating work. So the objective for this lesson, what we should be able to do by the end of it, is about, obviously, like the title says, calculating the amount of work that's being done when any two objects are interacting. So before we can calculate the amount of work being done in a situation, we really need to have a definition that we're very comfortable with for work. So work isn't a type of energy. It's not even a form of energy. Work is a transfer of energy. So when one object is transferring energy to another object, like a spring transferring energy to a ball, or a person transferring energy to a shopping cart, we are doing work in those situations. Anytime that a force is being exerted on an object across some distance, work is being done, energy is being transferred. For example, this box here that we have drawn. This box was experiencing a force across this distance x. Work would be done on that box. Whatever is exerting the force is transferring energy to the box. So work, while it's not energy in the sense that it's a type of energy, since work is about how much energy is being transferred, it's measured in joules. Now, I can calculate work by really looking at that force. Oops, wrong color. There we go. By taking that force that I'm applying on the object and multiplying it by the distance that force was applied across. Now, in order for our units to become joules, our distance has to be measured in meters, and our force has to be measured in newtons. Remember, a joule is the same thing as a newton times a meter. So if we don't use newtons and meters, our answer that we calculate isn't going to be in joules. So let's get some practice using the equation. We've got an example right here. Ben Travlin pushes a 20-kilogram suitcase with a horizontal force of 50 newtons across a distance of 35 meters. How much work did Ben do on the suitcase? So I'm going to color code some relevant information here. They gave me my force to be 50 newtons, and they gave me my distance to be 35 meters. So in my work equation, I know what I'm substituting for force and for x. Now, they did give me some extra information about the suitcase. They told me its mass is 20 kilograms. Now, in order to calculate work, I actually don't need the mass of the object. So that 20 kilograms, while it's good information, it's not necessary information for my work equation. So I'm going to get started by plugging in 50 newtons for my work and 35 meters for my distance. So 50 times 35 is going to get me 1,750 newtons times meters. And remember, a newton times a meter is the same thing as a joule. So the amount of work that was done on that suitcase by Ben is 1,750 joules. So fairly straightforward. The next problem, this try is a little bit more challenging, but I would like you to try it without seeing the solution first. So go ahead and pause this video and attempt it. When you're ready to check your work and see how you did, unpause the video. All right, I'm assuming that if you are watching this, that means you've attempted this problem already. So let's get started. A tired squirrel, with a mass of 1 kilogram does push-ups by applying a force to elevate its body 5 centimeters. So 5 centimeters is the distance that its body is moving. How many push-ups must the squirrel do in order to complete 5 joules of work? So 5 joules of work is a quantity that I would plug in for W in my equation, not for F, force. So remember, this is the equation we're working with. They've been given this variable and this variable. So that must mean that force is what I'm trying to solve for. So I'm going to substitute in 5 joules for work. My force is unknown. Now, before I plug in my distance of 5 centimeters, I have to convert it into meters. So I know that 100 centimeters is the same thing as 1 meter. So that must mean that 5 centimeters must be less than a meter. If I wanted to figure out how many meters it is, I would just have to divide 5 by 100. And when I do that, I get 0.05 meters. So this is what I will substitute in for x. So in order to solve for force, I need to undo what's being done to it. So I'm going to undo the multiplication by dividing by 0.05. But whatever I do on one side, I have to also do on the other. So 0.05 is going to cancel out. 5 divided by 0.05 is going to get me 100. And my units for force are newtons. Now, the problem didn't ask me how many newtons of force the squirrel is going to have to exert. It asked me how many push-ups the squirrel is going to have to do. So I have to take this 100 newtons and figure out how many push-ups is that going to equate to. So this is where the problem gets kind of tricky. Drawing a force diagram is going to be really helpful in this scenario. When the squirrel is doing the push-up, the force of gravity and the normal force have to at least be equal. If they're not at least equal, if the normal force isn't large enough, I should say, the squirrel's never going to move their body upwards. So whatever my force of gravity is, my normal force has to be at least that much as well. Now, I can find gravity by taking the mass of the squirrel and multiplying it by 10. So 1 kilogram times 10 means that the force of gravity on the squirrel is 10 newtons. So if my squirrel is doing a push-up, the normal force acting up on the squirrel has to be at least 10 newtons. So if my squirrel has to exert 100 newtons of force, and each push-up is 10 newtons, then I just have to divide that to figure out how many push-ups my squirrel is going to be able to do. So 100 divided by 10 means my squirrel is going to get to do 10 push-ups when they do 5 joules of work. Ooh, didn't like how that turned out. A little bit better. If you could get to this point in the problem where you were able to solve for force, that is a really good start. If you weren't able to translate that into push-ups before seeing the solution, that's okay. It's not the kind of problem that you maybe would have thought to do that on the very first try. So keep in mind that if you're asked a question that's maybe a little outside the box because it's not asking for a variable in the equation, you might need to draw a force diagram. And that could be what gets you to the very end of your solution. So that concludes our lesson on calculating work. Go ahead and move on to the aligned practice that goes with this lesson.